Yeah, thank you to IS for giving me the opportunity to speak. And the title of my talk is Affine Springer fibers in the small quantum group. But really what I want to try to give is a certain flavor of geometric representation theory, which is the area that I do research in. And this basically, I mean, as the name suggests, is trying to build dictionaries between representation theoretical information and geometric information, so that we can use techniques from each of the other side to solve problems on the other. And I'm going to try to give a flavor of this by focusing on some results I've been working on. So I want to explain the two sides of this dictionary in the case of my work. So in the representation theoretical sides, there's some objects known as Frobenius kernels, which is some certain algebraic group. I'll explain all this. And a small quantum group, which is something sort of similar in some sense. And in the geometric side, this should correspond to some affine Springer fiber. And in what way do they correspond? Well, there's certain things in the representation theoretical side that have some geometric interpretation. In particular, in joint work with Peshkov, Shan, and Basarov, we say that we compute that the center of this of the category of the Frobenius kernel, or more precisely a small quantum group, is related to the cohomology of this space in a certain way, which I'll explain. And in other work, in work of Peshkov, McGreen, and Yun, they relate further the category of representations of these objects with some category of sheaves on the geometric side. So the talk today, I'm going to try to explain these representation theoretical objects and the geometric objects, and then explain the connection. So let me begin by explaining just what is a representation. So a representation of a group G is just a vector space with a linear action of G, which can be rephrased as such a homomorphism as in the slide. But what's the idea of a representation? The idea is to linearize group actions. Group actions in general are complicated and nonlinear, but representation theory allows us to use techniques of linear algebra, like in so many other areas of mathematics, to approach the problems on groups and group theory. And so an example of this linearization of the most basic kind of representation is a permutation representation, where we have some set S with a G action, and we can construct a representation by just linearizing that action. That is, setting S to be the basis of a vector space and letting G act on this vector space just by linearly extending the action on S. But I'm going to be focusing not just on groups, but on algebraic groups, on affine algebraic groups, which are just groups, but in a different category. It's groups in the category of affine schemes. So it's an affine scheme and a group, and such that the two structures work nicely together. And it turns out that such groups are just closed subgroups of the general linear group, the group of invertible matrices, which means just that it's some subset of some subgroup of the general linear group that is given as the vanishing of some set of polynomials. And I'm going to consider a particular class of these groups known as reductive groups. I'm not going to explain what this means, but for those who don't know, you can think of examples as the general linear group, the special linear group, the special orthogonal group, groups like this. And the definition of representation just has to be adapted to this algebraic setting, where the homomorphism described before has to be an algebraic map, so defined by polynomials. Now, I'm going to focus on these Frobenius kernels, which are some groups in characteristic P, but I want to explain what happens in characteristic 0 and explain why characteristic P is different. So in characteristic 0, an algebraic group G is always smooth. And it follows from this, it follows from this that if you have some subgroup of a group that contains some infinitesimal neighborhood, it's actually the full group. And so by understanding just infinitesimal information of the group, you understand somehow the whole thing. So the idea here in characteristic 0 is passing to the tangent space. Somehow the tangent space of the group and an adequate notion of representations contains the whole information of the group, well, more or less. And using this, we can understand the representation theory of these reductive groups in characteristic 0, and it's basically, the result is that it is easy. And what does it mean that it's easy? Well, there is some irreducible representations, meaning there's no stable subspace on them, and every other representation is just a direct sum of these irreducibles. So once you understand the irreducibles, everything else is built out of them in the easiest way. There's nothing complicated past the construction of these irreducibles. But characteristic P is a whole other game. In characteristic P, non-smooth groups exist. And the particular one that I'm going to study is not smooth. It's not smooth. And to introduce this, first I want to introduce the Frobenius map. So the Frobenius map, probably the most important map in characteristic P. In the case of this of a group, turns out to be a group homomorphism. And where does this Frobenius map come from? Well, it comes from the fact that in characteristic P, raising to the pth power is an additive map. And so this Frobenius map is going to give us some interesting group homomorphism of the group, and we can ask, what is the kernel of this map? Well, yeah, this Frobenius map, let's say in the case of the general linear group in vertical matrices, is just given by raising to the power p each entry. Now, in an algebraically closed field of characteristic P, raising to the power p is a bijection. I can always take pth roots, and in fact, there's a unique pth root. So on closed points, this Frobenius map is an isomorphism. But taking pth roots is not an algebraic map. It's not given by polynomials. So the Frobenius map is not an isomorphism of groups. So it has some kernel, which has a unique point, but somehow it has some non-trivial infinitesimal infinitesimal information. It's a non-reduced scheme, algebraic group scheme, which somehow, in some sense, captures the infinitesimal information of the group. The thing that we were trying to do before with the tangent space in characteristic 0, somehow the only thing that it captures is this Frobenius kernel. It's like a first approximation. And when you want to understand something of the group, sometimes it's a good idea to try to understand information about this first approximation. And yeah, just a warning for experts, I wanted to explain this in this setting, but the results that I actually compute are for the small quantum group, which is some algebra over the complex numbers, which has, in a sense, analogous representation theory to this Frobenius kernel. But I don't want to go into this result, proven by Anderson, Jensen, and Circle, which is very deep theory. Okay, and now to the geometric side of this picture. So in the geometric side, there's two relevant spaces: the affine slide variety and a certain affine Springer fiber. Now here's the full definition, but I don't want to dwell too much on the precise definition. I just want to explain what the finite dimensional analogs of these, what the regular slide varieties, not the affine slide varieties, look like in the case of GLN, to give a flavor of these spaces. So in the case of GLN, this flag variety is just the space classifying flags. So what are flags? A flag inside a vector space V is just a set of subspaces V1, V2, Vn, each of one dimension and each included into the other. And this space, the flag variety, just classifies the set of such flags. And the Springer fiber just takes those flags that are stable under some particular endomorphism, E. And in the case of this affine version, the endomorphism that I want to take is this TS. And here S is some diagonal matrix with different eigenvalues in the case of GLN. And T is the parameter of these Laurent power series that appear here. But yeah, instead of the precise definition, I want to give sort of feel for what this affine Springer fiber looks like. So this Springer fiber, it has countably many components. So it's some infinite, in some sense, space, but each component is finite dimensional. In fact, they're all of the same dimension. And even more, there's some action of some lattice of some finally generated free abelian group, such that its action on the components is free and has finitely many orbits. So there's some finitely many components, such that everything else is just a translate of those components. And in fact, yeah, there's a bijection between translates of those and this lattice. And the example that I want to explain is in the easiest case, in the case of SL2. So in the case of the smallest group, well, smallest non-trivial productive group, this is, tori, trivial, whatever. In this case, it's just an infinite chain of P1s, right? So topologically, a P1 is a sphere. So this is an infinite chain of spheres. In some sense, it's like an infinite pearl necklace. And the translation, the lattice, is just the integers. And it turns out it's translating, but by like 2 pearls, so to speak, as opposed to 1. So this is the space that's going to be relevant. And then here's the results. So what does the result say? So if we denote by Z the center, well, really the center of a regular block. Again, I don't want to go into too many details, but the category of this Frobenius kernel breaks up into some smaller, as a direct sum of smaller subcategories. And this makes the center break up into some summons. But most of those summons are the same. And I'm just picking one of those that are almost all are the same too. And because the Frobenius kernel is a kernel, it's in particular a normal subgroup. And so has an action of the group by conjugation. And this action hence induces an action on the center. So we have a group action on the center. And then with this information, we can construct the following diagram. So here T is the maximal torus. So in the case of the general linear group, these are diagonal matrices. And so, yeah, this diagram just says that if we have some cohomology class of the affine flag variety, we can construct some G invariant central element. And if we have some translation invariant cohomology class of the Springer fiber, we can construct a T invariant element of the center. And then the ideal result is this conjecture, which is part of ongoing work, that not only can we construct the central elements like this, but somehow you get all of them like this, namely the T invariant elements of the center are precisely the translation invariant cohomology classes. And on this set of translation invariant cohomology classes, we have an extra action of the Weil group. So in the case of GLM, this is an extra action of the symmetric group. And if you take invariance under the symmetric group, this should exactly correspond to these G invariant central elements. And as so often in mathematics and in geometric representation theory, this result actually has a surprising connection to other areas of geometry, namely the Hilbert scheme of points in C2. So yeah, in joint work with Losif, we proved that this action, this extra action of the Weil group, of the symmetric group in the translation invariant cohomology classes is actually trivial. And so assuming this conjecture, this would imply that the G invariant center is equal to the T invariant center, which actually implies that the G action is actually trivial on the center. The action of the group is trivial on the center. And the result of Losif actually depends, and in fact is equivalent to some result of Feynman, his proof of the n factorial conjecture, which in some sense bounds how complicated certain singularities are related to the Hilbert scheme of points. So this result basically says that the action being trivial on this center is precisely corresponds to somehow these singularities in this related to this Hilbert scheme of points being not too bad. And an interesting question would be to understand in the other groups where the action is non-trivial, can we say something more precise of the non-triviality of the action? How is this related precisely to these singularities in the analogs of the Hilbert scheme of points for other groups? And then finally, I want to state this result in the original dictionary, which is work by Veshukatnikov, McGreen, and Yun, which relates the category of sheaves, some category of sheaves on this Affine Springer fiber through causal duality. Again, I don't want to explain what that means, but in some sort of relation between this category of sheaves and some category of representations of the small quantum group. And this again fits into this dictionary, connecting these two sides, and I hope more or less this explains a bit of the flavor of geometric representation theory. And yeah, I will leave it there. Thank you.
Any questions for the speaker?
Yeah, what is the small quantum group?
Okay, so the quantum group is some deformation of the enveloping algebra. Okay. So if we take the tangent space of a group, that is the Lie algebra. We can take some algebra related to this, known as the enveloping algebra. We can deform this algebra with a certain parameter, Q, and this gives us quantum groups. And we can specialize these for generic Q, this deformation parameter, this algebra sort of behaves as similar representation theory to the enveloping algebra. But if you specialize at p root of unity, at some root of unity, this parameter, some more interesting things happen. And so, right, so if we specialize at one of these p roots of unity, this algebra is going to have some interesting finite dimensional subalgebra, and this interesting finite dimensional subalgebra is the small quantum group. And as I said, by work of Anderson, Janssen, and Sorbo, somehow this is a characteristic zero analog of the Frobenius kernel. I mean, yeah, basically the idea is they construct some category over, well, the integers or some localization away from finitely many primes, but basically over the integers, such that it specializes to this small quantum group representation in characteristic zero and specializes to the Frobenius kernel in most finite characteristics. So that's basically what small
it's more than enough. The small means you evaluate in Q at p roots of unity. What's a small?
Small means that it's the finite dimensional. If you evaluate at p roots of unity, there's there's many versions of the quantum group, but all the others are infinite dimensional. But there's one version which is a sub algebra of the usual quantum group, I guess. Well, yeah, let's say yes. A subalgebra, finite dimensional subalgebra, which is of interest, and somehow, in the same way as this Frobenius kernel is some sort of infinitesimal neighborhood of a full group, this small quantum group is some infinitesimal neighborhood in some sense of this quantum group. I mean, by analogy, I guess.
Thanks.
Any other questions for the speaker?
Oh yeah, I have a question. I have a question. So is this root of unity that you consider, is it all the prime to prime or can be not prime?
Yeah, in prime. I've just thought of it in prime, and yeah, if you consider it in even even things are going to change drastically. So for simplicity, it's a prime. But
No, but suppose we take p square, for example, p odd, p square.
Yeah, I haven't thought of the details. I just stacked the prime for simplicity in many of the steps, but I'm sure some statement can be said about those as well. But I haven't thought they were like I haven't thought it through.
All right, let's thank the speaker again.